I'm using fraud as an example here because it should be relatively easy to understand. I hope so. We actually, some of the first use cases that we use in graph databases were in the fraud space. And the reasons are pretty obvious. So this is globally, these numbers are a bit old. It's actually probably about 3 times this figure if you really look at it, if you include things like anti-money laundering and other things. But just for credit card fraud alone, people are spending about $2 billion a year, banks, card processing, payment schemes, to try and detect fraud. They're not very good at it because they lose about $50 billion a year to fraud, which is unrecoverable. A lot of this comes straight out of the profits of banks, so not surprisingly, they're quite keen to fix this. But the difficulty they have is that they're very much a regulated industry. They can't just do anything. They can only change very incrementally. And so the idea of using our technology to help with this was something that they liked the idea, but they were worried that the regulator was going to not be very happy about it. So the reason that they came to us, it wasn't out of sheer desperation, but nevertheless, there had been years and years and years of talking about artificial intelligence, about machine learning, about what they can do with the data they had. And really everything was, particularly once you get into the deep learning area, there was only a very limited amount of extra juice that you could squeeze in terms of being able to predict fraud. One of the problems with payment fraud is that it's relatively rare. You're talking about 0.1% or less of transactions are fraudulent, and that means it really is that needle in the haystack problem. The other is that a fraud doesn't stand up and say, I'm definitely a fraud. It can take anything up to 3 to 6 months to find out whether something really was a fraud or not. So the problem of false positives is a big deal, is how do I allow people to use their credit cards, but still try and protect them from people who are being fraudulent. The tuning of machine learning algorithms, I think we've seen it probably, we've reached peak machine learning in many ways once we got through to neural networks and things like that. And that was the point where the banks were going, is there an alternative here? Unfortunately, we popped up to help. And what we said to them is, you've probably gone as far as you can with your algorithms at reasonable expense. The problem you've got is that you're not actually, it's the data that you're putting into them. And they said, well, of course you're going to say that because you sell graph databases. But we said, no, just bear with me a moment. Generally, data, particularly data in the real world, it's a whole network of information. It's not just individual information. It's not about an individual person. It's about who the person interacts with. It's about who the transactions, where they go, where they happen, all of the context around a transaction. Are you on holiday? Is the transaction happening in the same place as the person who owns the credit card? There's lots of contextual information that can help when you're trying to deal with fraud. But it's this relationship information, which is the key point here, is actually extremely difficult to pass on to your machine learning systems. So instead, what people do is they just give it the basic information, the credit card, the transaction information, really the very limited information that they have around the individual piece. And this is true generally when we're trying to model the real world in a standard data stores like relational databases. You can store the information, but what you can't do is query it. You can't query the relationships. You can't say, what are all the dependencies on this particular piece of information? How does it all link together? Maybe if I know that you're the friend of a friend of somebody who robs banks for a living, then there's probably a slightly higher chance that you actually also rob banks for a living. That idea of being able to look at the entire network to be able to get some idea of whether you're a good credit risk or not, whether a transaction's likely to be fraudulent, it all requires an ability to ask these sorts of questions, which are very difficult to do with a relational data store. So as a result, you can't give the data to your machine learning doesn't see it, and so your machine learning therefore can't find it and go, wait a minute, I know this guy, this transaction is a bad transaction. Or more valuable to them often is, I know it looks like a fraud, but actually it's not. The false positive problem is the biggest problem for banks, because of course, if I can't use my credit card on holiday, if it's blocked, I'm probably going to change banks. It's going to spoil my holiday, I'm not going to be happy, and they're not just losing money on the individual transactions, but it also means that I'm never going to want them to use them again. Equally, I don't want a bank that lets anybody steal my credit card, go overseas, and just start spending like crazy. So finding that balance is a really difficult problem. This is a clear opportunity to improve. I love this picture. Our head of industrial solutions uses it a lot, and I stole it off him. The point here is that in your data store, what you can supply to your machine learning tends to be structured like this. It tends to be all of the things of the same type in one table, and then all of the things of another type in another table. And the relationships between them aren't really, it's very difficult to query those relationships, even if they are in the data. Generally, all you can get out of it is this. Whereas, of course, this is an indication of the extra information that is available when you look at things holistically, when you look at things in terms of their relationship to each other. And so the opportunity really is on whether we can somehow get this into your fraud detection systems, which are often machine learning systems, or however it's structured in the bank. Just to really push the point home a little bit, in a relational database, you can see a product, a customer, you can see orders, suppliers, locations. There is linkage information available in the database, but it's it's in the background. It's if you do SQL, and I'm sure that quite a number of people here do, then the idea of joining tables is something that you do all the time. The idea of self-joining tables back to themselves to find the relationships, for example, between accounts, or indeed to find these multi-hop relationships, that's something that is extremely difficult to express in SQL and ultimately is very slow. Enter the graph database. It doesn't look terribly different. Products have got products, customers have got customers, orders have got orders, and this is the point, is that the difference here is not so much in these big blobs, which are the tables. The difference here is, first of all, the links are very explicit. They're no longer implicit foreign keys, which don't have any identity, really. Now they have identity, they can have meaning. If you get into the semantic world of graph, then they literally only have links. That's their entire life. For us, it's first of all expressing these links, which is nice because so the links are considered first-class members, things that we can actually query directly. So we still have our facts stored in vertices, so it's not too difficult for us to import data from existing databases. The relationships now we've got as first class, but the reason we're doing all this, the reason that we're going to all the trouble, is so that we can specifically analyze the information in the network, this ability to be able to get the data out that is at multiple locations away from where it is. The difficulty we had was that even though we had that information, how am I doing? 10 minutes. Even though you have that information, it doesn't fit into your existing data processing systems. So we haven't actually solved anything, really. Not enough, because then people think, oh no, we're going to have to change everything. We're going to have to now, we need new machine learning that understands graph databases, and that kind of doesn't really exist in our bank. And if we did change it, the regulator's going to come along and go, oh, so you've got a new model. Prove to me that your model isn't saying nasty things about women versus men. Or it doesn't show bias, which is a legal requirement in the US and indeed in Europe indirectly. It doesn't, or in other ways that it is actually not really detecting fraud, it's actually detecting other things that are illegal effectively because you're segmenting society in a way that is not appropriate. And ultimately for the bank, of course, is lost business. So, they don't want to do it either. This designed specifically to analyze the information in the network, great, but the machine learning systems have to be able to consume that information somehow. They have to be able to use the information, and that's what this talk is about. So we're good. We just need to feed the graph information into our ML models. Yes, we'd like that to be true. What we found was this was just not that easy. We worked with a number of extremely large banks, And the first thing they said to us was, yeah, we like this idea, we like having this, but we also like our existing rule-based models, our machine learning models. We've got them approved. It takes 3 years to get approval. It's really painful. We don't want to change them. And we just can't use your graph, so thank you. Ring us back in 3 years' time when we've worked out how to do this. And this is why machine learning only understands tabular matrices of data in rows. It's been designed for rows of data. If you know anything about deep learning, it talks about TensorFlow. Tensor, what's a tensor? Tensor is a row. It's a row of data. And so each of our data items are effectively considered separately. They're considered independently. It has no way of thinking about the links between the information and using it as part of machine learning if we just go with what we've got, which kind of leaves us a bit at square one. If you look at connected data, it looks rather different. It's very much the blue. These are the bad guys, the blue ones. Machine learning only understands tabular matrices of data in rows. Yeah, we know that. And so we were stuck, but then we thought, are we? Let's look at actually what we're getting from the graph database. Let's see whether we can do something else instead. So the information we want from the database, so why you would use a graph database is that you can ask, these are analytic questions, it's not just about getting the data. So generally, and it's provably true, the closer an account is to an account that's suspected of fraud, or the more likely it is itself of committing fraud. It's not just about fraudsters. You could say exactly the same thing about people buying stuff. The closer you are to somebody who's bought product X, the more likely it is that you will also buy product X. And so that's an example of another use case which uses pretty much the same techniques. So in graph analytics, we have ways of doing this. We can run an algorithm called all pairs shortest path. And what it does is it tries to work out how far away everything is from the nearest fraudster. It is difficult to run. It's incredibly difficult to run it in an SQL database. Most graph databases have difficulty doing it at scale, obviously. Ours was designed to do that. But the point is that once you can do that, and if your data size is appropriate and you've got the power, then you can run this once over your data, and you've got this information from the information that you've already got in your database. And so the trick which we went with was this idea of embedding. If you ever deal with graph algorithms, if you ever deal with particularly statistics, there is this concept of embedding. And just before our talk came on, I had a small argument about whether I was using this appropriately. I'm going to use it in a slightly... So if there are mathematicians in the room, yeah, okay, I understand. It might be a little bit imprecise. But the basic idea of embedding, as I am treating it today, is that you're taking what is very high-dimensional data. So the data is all over the place. It's got many, many dimensions. And you're squishing it down to the set of dimensions that you want. In our tabular set, we saw that it's effectively 2-ish dimensions of data, but we're dealing with these massive dimensionalities of data. Actually, it's almost infinite dimensional, but the point is, how can we squish it down? How do we get it back into that 2 dimensions? And so embedding here is, well, why don't we just put the distance to a fraud on every vertex? We'll just squish it down and put it on. And the vertex here is just, remember that dot that the machine learning can handle. It's great. So we thought, okay, that works. And then centrality. This is PageRank. If you ever do PageRank, the idea is which web page is the most important page. It's calculated using algorithm, usually PageRank, although there are newer ones now, but Larry Page, who can give me a job anytime if he wants to, very rich man. It all comes down to this, which is his thesis, PageRank, which was his ability to recommend things not just on the content of the page, but actually who points to it and says, this is a great page. And what it does, but the great thing is it creates a score which says it's this significant. This is the significance, the centrality. And we thought, well, that's another score. Great. So we'll embed it. Same trick. We just add the score onto the vertex. I got lazy, I did this earlier, I've only put a few scores here, so you'll kind of imagine that I've got scores and everything. But you see the point is that by having different scores on here, now we've got the centrality, we've got it on all the vertices. What we're doing is adding contextual information and putting it onto the vertex that's the subject of it, and therefore moving towards this idea of maybe now we will be able to actually use the ML that we want, which is kind of, hopefully you'll see, it should be fairly obvious that this is where I'm going. Community is another one. An account that is in a community, so in other words, has not only linkage, but is also quite close, so it's like a combination of the two things we saw earlier, is more likely to be involved in fraud. And when we say community, we don't just mean they live next to each other. It could be that they have some other features in common, some other information in common that means that they're close in terms of they're similar. And that could be any linkage through the network. And there's this lovely algorithm known as the Louvain graph algorithm, or Leuven, depending on where you come from in Belgium, which does this very well, and it can do it on enormous amounts of data, and which is good for us because it means that we've got a possibility of doing something quite sophisticated across large amounts of data if you've got a scalable, great graph database. What do? Guess what? We embed it. We just add a number. We say, right, you're neighbor 1, you're neighbor 2, you're neighbor 3, you're neighbor 4. And we just basically put the name of the neighborhood in the graph. Each time we're bringing this information towards each of the nodes on the graph. And then we're going back to, remember, this is our tabular one, the one that we said how sad it doesn't do network stuff. But we are now putting the context, we're encoding it, which is the point of the embedding, into that data. Now we've got our account ID, doesn't tell us very much, but we've got distance to fraud, we've got PageRank centrality, we've got Louvain community, all of these, and any other graph algorithms that we can think of. That, by putting that in the particular, every single vertex here, every piece of information, thank you, we are now moving to the point where we can actually perhaps use this. And you just feed this to your existing machine learning pipeline or whatever you're going to use this for. You can actually use it directly. Sometimes, particularly for recommendation engines, you might just use the score and just order things, just like Google does for web pages. You can order products in the same way. But certainly from the bank's point of view, they liked it because their original machine learning pipeline can consume this data directly. Means they don't have to ring up IT and wait 6 months. They can actually just basically feed it straight into their data science teams. Data science teams know what's going on. They're okay with it. We do have these new feature columns. So the idea is we have these network features. So we're actually improving the world a little bit. We've at least put the information in, which encodes the information we previously missed. This provides new information for your machine learning with no need for model changes, which was, again, comes back to that regulator point. So this is the IT bit. We don't want to change our systems. We've got the new information, but this is the regulatory bit. You don't need to change your model. You don't have to worry too much about regulators causing you too much hassle, because generally, when it comes to data science, the regulator's kind of okay with this approach. In a few years' time, there's a whole thing about transparency and observability that comes along later, but that's tomorrow's problem, not today's problem. Therefore, and this is, it can find more frauds with fewer false positives. And you'll see there's a bit of a leap there. But nevertheless, generally, if you're working in data science, then one of the things all you want is more features. You throw everything at it. The whole point of machine learning is let the machine do the learning. And that means get everything, just show it everything, let it decide what's significant or not, let it tell us what actually matters. Having the information in the first place is everything. You don't then have to worry too much about engineering your data, worrying about whether your data is any good, whether you've got the right data anymore, because you just throw all of it at your machine learning and let the machine learning sort it out themselves. You might be using one of the AutoML products, of which there's about 10 outside. which will literally do it all for you. You just throw the data at it. And they love this stuff. For them, it's almost a push button. It's also running through their existing systems. It's just a table of data. Everything just works. If you want to say what that looks like, right, first of all, I said without qualification, and it makes the world a better place. We've got 4 tier 1, that means big, US banks using TigerGraph in production. And they are doing exactly this, generating graph features for their existing AI fraud detection systems. This is over terabytes of data. They run this overnight. They use that to train their models. They then use those models in their credit scoring and credit applications. Synthetic identity fraud, big problem in the US. Less of a problem over here, but nevertheless, 20% improvement in detection. And when you're a data scientist, improvement means more accurate. You can make that trade-off. You've got more room to make the trade-off. It doesn't mean that they're literally finding 20% more frauds, but it means they could. But what's better is that they can distinguish the real positives from the false positives. Another one, we like them very much. We get them to speak at our conferences. Said it was the best technology ROI from their technology investments that year, possibly ever. $100 million per annum from day one projected on the basis of they're able to prevent mortgage fraud in mortgages, very high value loan application fraud. JP Morgan Chase, the only one who allows us to actually name them, although we can't say what they do, but it's somewhere in there. And it said the only thing you're allowed to say about us is that we gave you a Hall of Fame Innovation Award in 2021. I think 3 products a year get this, and sometimes no products get it. And TensorFlow was one of those, so we're kind of up there. We were very pleased about that, and they talked to us. And the reason they like it is this. You've got core systems, data lake coming in. Normal machine learning feature generation is here. We just add on the side. We just bolt onto the side. Those features then get brought together in the rows, as we've seen, straight to the fraud detection application, which is relatively unchanged. Now, this talks about ML feature generation. There is a model generation element in here as well, but the main point is that this piece, one extracting features from the existing data, this one generating extra features and bring them together, means that everything else just follows without them having to change too much, which is a big deal. It isn't just fraud. Exactly the same techniques work for any network data. And I argue, well, I would, but nevertheless, I do argue that all data that describes the real world is effectively networked. There's almost no data that lives by itself that doesn't in some way relate to something important. It can be some meaning linkage, but it can be direct linkage, so dependency networks in a flow of data. If something breaks upstream, it's going to affect something downstream. That idea of having flows, and this is used for that. So customer product data, retail recommendation. You bought it, so I'll buy it. Supply chain parts data. This is very much for risk and cost optimization. We sold quite a bunch of this to JLR. We're talking to a number of, I think we've also sold it to Ford and Toyota. We hope to be selling that to some of the German manufacturers soon. IT network maps for cybersecurity is a relatively recent one, but again, the idea is to be able to find the paths where risk applies, but also to be able to work out what is the risk of a particular path being taken. In other words, what's the likelihood? If there's only 3 steps to compromise a system, that's going to be more likely to be compromised than something that has 10 steps. And all of the same ideas apply, and it's possible to use machine learning to augment that if you've got history as well that you can apply to that. And this one's very, very kind of data techie, data lineage networks for compliance and change sequencing. That's about, if you're, say, migrating everything to Snowflake, which I'm sure 50% of you are, then that involves changes to data systems while they're in operation, which means there is a huge risk that when you make that change, it's going to break something. The idea that you can find all of the effects, all of the impacts of a change, that's the first thing you can do with the graph database. But when you add analytics to it, you can effectively score the whole network for that risk. And then you can think, what's my next best action? So just like next best product, you can go for next best action on changes, and you can say, given your 10 changes, that one's hardly any risk at all, go for it. That one's going to break the world if it goes wrong, send it to an architecture board for review for 3 months before you even touch it. That kind of ability to plan ahead and score on that basis. And of course, in your use case here, the algorithms are completely generic. If we have network data, we can chuck the algorithms at it, we can score it, you can throw it at your machine learning, and who knows, maybe it'll find something. Maybe it won't. It's a very low cost, low risk, very fast way of looking for the value where the value exists. And as I say, we're quite confident that the value can be found, but what we're trying to do now is to make it so that it's consumable, so that you can just give it a go. Easy to try, given the right database. I'm trying not to be too salesy, but I'll work. It's good. Importing the data, run the graph analytics, export the data, feed it to your machine learning, and have a look. As simple as that. That can be done in days. We've got a software as a service, free layer, tgcloud.io, where you can try this stuff out. It's got examples on there. You're welcome to try it. Equally, if you're a bit more serious or you want us to do some of the work for you, then just give us a call and we'll talk about it first. But the point is that you can A/B test it before you start committing significant funds, before you're looking at having to change too much, which is generally the case, which is usually the problem. Everybody wants to innovate, but it costs too much, and then you don't know whether it's going to work. The idea is to make that easy. Of course, I had to do this slide. We're bigger, faster, and better. The scale thing is kind of a big deal because it's very difficult to do analytics at very large scale. All of our algorithms are open source in the sense that they can be changed, they can be examined. So at least you can make sure that what we're doing, what we say on the tin, actually it's doing it. So it's relatively easy to understand. We've seen that. 20% improvement. 20% improvement for fraud is great. If you think about that, $50 billion, that's a significant amount of money. 20% improvement anything is usually quite good. And so there is definitely a prize to be won here. And this is our standard marketing message. Thank you. Yeah, they pay my bills. But we did. This actually is a big deal. We were very, very proud of that. That was something that was 2 years of effort. And what you're seeing in this presentation is pretty much what we found out from that, but also what we found out from Bank of America, from a number of other banks that I'm not allowed to name, where they went through this process and they found it kind of worked for them. I would recommend have a go. And I think that's the end. Have I left any time for questions?